real important question. Does there exist a linear combination or more than one linear combination of a given set of vectors that add up to the zero vector? It's going to be related to the important concept of linear independence, spanning sets, and so forth. Very important idea. Okay, well, let's just illustrate that using what's becoming kind of our canonical set of three vectors and R3, and R2, sorry. Okay, so if there's a linear combination of vectors that adds up to zero, well, what do we mean? Linear combination of the given set of vectors. Well, linear combination of this set of vectors is like C1 V1 plus C2 V2 plus C3 V3, a sum of multiples of those vectors. Is that linear combination zero? Or can we find C1, C2, and C3 that make this zero? Okay, so that leads to the equation C1 V1 plus C2 V2 plus C3 V3 equals 0. And as we've seen, that can be written easily as a matrix equation. Now, this matrix equation is equivalent to a set of simultaneous equations. And again, we're assuming that it's clear why this is the case. Okay, it's equivalent to this system. And this system can be represented, so let's write an equivalence here. This system can be represented by the matrix the augmented matrix here. Now, clearly, the system can be solved by elimination. We can add 2 times the second, sorry, we can add negative 2 times the first, no, negative 2 times the second equation to the first, and eliminate C1. But then we're going to have two equations, or we're going to have a single equation in C2 and C3. And that equation is going to have a free variable. And since that equation will have a free variable, we see that there are going to be solutions. But that's one way to look at it. We could do that by elimination. We can do the same thing by row operations on this matrix. Okay, now row operations on this matrix. And let's hope I do this correctly, but to be complete, I'm going to switch the rows so I have a 1 in the first column up at the top. So I'm going to say we have 1, 2, 5, 0, 2, negative 3, 4, 0. This leads to 1, 2, 5, 0, 0, adding negative 2 times the first row to the second. Negative 2 times 2 is negative 4. Add that to negative 3, we get negative 7. 2 times 5 is negative 10. Add that to 4, we get negative 6. Now, we could take 1/7 of this row and add to this and so forth. Reduce this all the way down to our canonical form, our Gauss-Jordan form. Jordan, it's always pronounced Jordan, you know, a couple hundred years ago when I was in school. And it's the way I tend to pronounce it. But whichever. We could reduce it all the way down, but at this stage we see that we now have a system that's equivalent to C1 plus 2C2 plus 5C3 equals 0, and negative 7 C2 minus 6 C3 equals 0. I was tempted to change the signs there to make them both positive, but no need. And we see that this equation, we can't reduce this any further. This equation is going to have a free variable. Let C3 equal T. Then C2 equals negative 6/7 T. And having C2 and C3, C1 is then going to equal negative 2 times negative 6/7 T minus 5 times T. And we can express that and, check my arithmetic. But it looks like we have 12/7 T and negative 35/7 T, which would give us negative 23/7 T. And this tells us then that, I'm out of room here, so I'm going to have to sneak it in over here. This tells us that C1, C2, C3 is equal to T multiplied by negative 23/7 negative 6/7 1. Now we can put that in a different form. We can multiply everything by 7 and we have negative 23, negative 6/7. Since T is arbitrary, we can write this in the equivalent form: T times negative 23, negative 6, 1. If we like 23, 6, negative 1, any form that's a multiple of this form, and the value of T is going to absorb the multiplier. Okay, so the point is now that we've determined that there is an infinite set of C1, C2, C3 that makes this 0. So there are infinitely many linear combinations because every C1, C2, C3 in this set, as long as we have some multiple of this vector, or this vector, is going to give us a linear combination that's 0. So we have infinitely many linear combinations as indicated here. This system, or this equation, is called a homogeneous equation. We have just zeros over here. And that makes it, I got too many zeros there. Hopefully you caught that, and hopefully if you did, it didn't cause you too much confusion. But of course, when we multiply a 2 by 3 matrix by a 1 by 3 column vector, we get a 1 by 2, not a 1 by 3 column vector. Okay, again, it's called a homogeneous system because we have zeros here. Having zeros here means that really all we've got to do is reduce the matrix of column vectors for V. Remember that this, and this are column vectors, are the vectors. The columns of this matrix are these vectors. This column is just zeros. If we had specific numbers over here, that would change things a little bit. It would give us specific numbers over here, and that might have some effect on the C1, C2, and C3. Okay. Important terminology. This is a homogeneous system. And again, that has its implications for the nature of your solution.